Let's move on to static libraries. So one of the things of why we have this all business of separate compilation and linker is you want to allow code reuse, right? The reason you want to split your code into multiple files and so on is because you want to reuse that code. For example, let's say you have written various data structures implementation, right? And you want to use them across your different uh, projects, right? What you can do is you can essentially, one way to distribute is you can distribute it as source, right? But distributing it as source has a problem because um, it could lead to IP issues and so on. The other option is you can combine all of that into single object file, but that has a problem because uh, if you modify something, everything needs to be recompiled. So for example, let's say you have uh, A.C, B.C, C.C, D.C, just and so many of them. If you change A.C, you'll have to change everything else if you wanted to package everything together, right? So typically you will have your code organized into multiple object files. And what you can do is you can still create a logical unit of these multiple object files using a static library, okay? So static library is nothing but collection of object files which has an index which says, okay, where are things located, okay? And on Linux, they typically have .a extensions and stored as archive, okay? So how do you create static libraries? You have multiple object files, you give it to a utility called AR, which will create a static library with extension .a. Okay, so I can have something like this: AR, RS, lib. So essentially, I'm saying create lib my.a from obj1.o to objn.o, and there are a few functionalities with respect to incremental updates. Now, how do you actually use it? So let's say you have created. So let's say you have this foo.c bar.c. I have created a lib my.a, which has these two definitions, and I want to use it in my program, right? So the way I would do that is I will do gcc myprog.c, right? I have to tell linker where the share static libraries are present using this -l path, right? So I'm saying it is present in the current directory, and the library name is -l my. So this lib prefix is kind of omitted when we give -l, and the naming convention is kind of fixed. You're supposed to name your static libraries this way so that you can use it in -l command, okay? And it will essentially produce a.out. Okay, so what essentially happened is instead of giving gcc myprog.c -o myprog.o, gcc myprog.o, foo.o, bar.o, and so on, we kind of collected all of them together into a single archive, so it makes it easier to use. Okay, now if I slightly change my command, like I give something like this where I say gcc -l dot -l my myprog.c, this would actually not work. Okay, in most of the linkers this would fail. Okay, and the reason it fails is because the resolution of symbols in static libraries work slightly differently. Okay, so typically what happens is the archives that are produced may have many objects, right? So if you consider a big library that was given to you by someone, it may have thousands of objects, right? And you don't necessarily want to link all the objects, because what that would mean is it would mean that your executable is big, you have unnecessary code that is present which is not even used. Okay, so we want to ideally get to a situation where only the required objects are linked together. So libc.a, which is the libc, which provides implementation of malloc, std string, and all those kinds of things, has 1500 object files, right? But it's not that in every program you might be using all of those functionality, right? In some programs you might be using strings, in some programs you might be using malloc, in some programs you might be using both of them, right? So you don't want to pay for what you're not using, right? So the way linker works is for static libraries, it allows you to extract only the objects that are needed. Okay, And typical implementation of linkers algorithm is something like this. Okay, so whatever is the command line that you have given, right, it would scan the .o and .a in that order. Okay, now let's say you have given gcc a.o, so it would take a.o. Okay, it would kind of start linking it, and it would note down what all symbols are unresolved in this. Okay, and if it looks at the next object, and if it doesn't find uh, definition of the symbols that were unresolved, then it might just skip it. Okay, and in the end you essentially get the linked things. Okay, so think of it this way, that every time I'm linking something, the extent definitions must be satisfied by something which is coming in the later in the command line. Okay, so for example, oops, sorry. So if I have a.o and a.o is calling some of the libc routines, then if I give libc in the end, then when a.o is processed, linker would know I need definition of malloc, I need definition of strlen, I need definition of memset. And when it sees the archive, it will look at all the object files which are present, and it would see which one is providing me definition of strlen. Okay, let me pick that. Which one is providing me definition of malloc? Okay, let me pick that, and so on. But it would not end up picking something which is providing definition of some other thing, right? Let's say calloc, which might be, say, in some other object file. Okay, so because of which, in this particular earlier case which I showed, it actually failed, because what happened is I gave to the linker the library first. Okay, so what linker saw is, okay, I have an archive. Okay, none of this is needed because my proc.c is not using it. And when it saw the myproc.c, there was nothing beyond that which was satisfying the definitions. So it actually fails with undefined references to malloc and so on. And you can actually examine the archive contents. So you can do, there is something called as nm, which we didn't see so far, but nm kind of gives you the index of where all things are present. And it can also give you which symbols are defined in which object files. So linker can essentially use the similar logic to detect which symbols are defined to figure out which definitions are provided here. Now, what are the disadvantages of static libraries? Well, one is, once you link static library, it is part of your executable, right? And once it is part of your executable, it is private to your executable, right? So imagine the number of processes that are running, which might be requiring to use strlen, right? If that code is duplicated in each of the process, then you are essentially losing out that benefit, because all of them are trying to share that code, but essentially it gets duplicated if you statically link, right? If you fix something in static library, so let's say libc was a static library and malloc was fixed in that, then unless your application is relinked with that updated library, you will not get that fix. Okay, so you'll have to relink your code to get the fix. And essentially we have shared libraries which can help overcome this. Okay, unfortunately we are out of our time, so we might have to stop here. Ramakrishna sir, what would you advise? I don't think I will be able to cover dynamic linking.
Right, I agree, Girish. I don't know. Maybe if the participants have energy, maybe I mean, how long does this take? This is very important. Dynamic linking is fundamental.
Yeah,
So,
I mean, I could quickly try to. I mean, if I can skim through it a bit fast, I can try to cover it in 15 minutes or so.
That would be nice. I think this is something fun, so important. I think they would want to really learn it from you. I don't know. Is everyone okay with it? Can someone please show hands, raise of hands? Is very important, you know. Okay, Girish.
It's very important, but can we schedule another session? Because I think it would be very nice to see dynamic linking and some aspects of program execution on GPUs, especially with GPUs coming up. So yeah, there's a lot to cover. 15 minutes is not really enough to understand these beautiful subjects.
I agree, but at least can we proceed towards dynamic linking for now? We about the further session. I don't know when we can schedule. Let me see. Let me. Yeah, how can we schedule that? Um, but at least my request is we can at least proceed with dynamic linking right now.
Okay, so let's do this. Let me proceed with dynamic linking. I'll try to cover it.
Thank you.
If for some reason people still feel that it was covered in Rush or they didn't get it, or we still have more material to talk about, we can see if the schedule permits. But yeah, I think the other days are already packed, so I'm not sure if there is much room. But anyway, let's not wait, and let's spend 15-20 minutes more to at least let me touch base on this topic. So shared libraries is essentially trying to address the problems which we just saw with the static library, which is essentially somehow able to share code across processes, right? And I need some way to fix bugs without having to change the application. Okay, and the process where the shared libraries get linked to the application is known as dynamic linking, and it is performed by dynamic linker, which is different from the linker that we have. I mean, it's similar in terms of the operations, but it's a separate component from what we have been seeing so far. Okay, and Linux refers to these as dynamic shared objects, and they typically have .so extensions. Windows will call them as DLLs or dynamic link libraries. Okay, I'll skip this part which talks about how to create the shared library because this is mostly the command interpretation of it. How to use shared library varies a bit. You might see these kind of errors when you try to run something which says error while loading shared libraries. So the way this works is you have to actually install shared libraries. Okay, so when the process actually executes, the dynamic linker needs to figure out where the shared library is. So you'll have to install them. Install them could mean that you might have to copy it in some standard locations like user lib and then run ldconfig, which will update it. Or you can hard code path to it during the compilation. Or you can use an environment variable called as ld library path to specify to the dynamic linker from where it can see the dynamic library. Okay. If you do any if you have any executable, you can do a command like ldd a.out, which kind of shows that what are the dependencies. Okay, so let's look at how the DSO looks. Now, again, the good part of ELF is ELF, the same thing is capable of representing the DSOs. So the type here would essentially change to dynamic shared libraries. Okay, so whenever I create a shared library using gcc-shared, and if I read the header for libmy.so, it would essentially be a dynamic shared object file, which is different from the, which is structurally similar as ELF, but it is slightly different from the relocatable object file that we saw than the executable files. So this is the third kind. Okay, and the entry point address, as you can see, for shared library is different. It is not the _start one which I was showing earlier. Okay, and this one actually can, what this is saying is within this ELF file, the text section starts at 3D0, not that 3D0 is where it must be loaded. Okay, the loading aspect of shared libraries is slightly different. So if we look at, let's say I have this code, right, and I have compiled this using -shared. The text section would look same, right? There is a relocation section which says that which is specifically known as .rel.dyn, which is essentially holding the relocations that indicate how the addresses of these variables must be resolved. So for example, this is saying that address at location 500, we must patch address of GBL using this relocation R38632, which, if you recollect, was the absolute address of GBL. Okay, so there are some new relocations that come up in the dynamic shared libraries to resolve the references within the shared libraries. Okay, and these are essentially what I was pointing out, that these are patching these instructions. So whenever foo references GBL, it is patching the address just like what used to happen. But in this case, the address of GBL is not known because remember, the shared library might be loaded at different addresses. Okay, so the address of GBL is not known until it is actually loaded. So this would be resolved by the dynamic linker. Okay, now this scheme which I mentioned is where the DSO is using the relocations. Okay, now this is a straightforward way to implement DSOs, where I generate the text section, all the references within the shared library have relocations, and I generate relocations for patching them. Okay, and this works exactly similar in how it would have worked in the compiler generated relocation case. But there is one problem, is unlike the earlier relocations which we saw, right? These relocations which are generated need to be resolved at load time, because the shared library is not part of your executable. When your executable starts running, that's when the dynamic linker will come into picture and it will load the required shared libraries. So this relocation processing needs to happen at the load time. That means if you have many relocations, then your program would actually start up a bit late, because those relocations are being resolved by the dynamic linker, because it's a runtime overhead on your application. Okay, and more importantly, these relocations which I showed, right? So let's say a shared library uh, uh, is, so the same thing which I had showed here. So let's say this is a shared library and I'm trying to use it in my process P1. So process P1 runs and the shared library starts at address, let's say 500. Okay, that means address of GBL might be somewhere within 500 to whatever is the size of the shared library's data segment, right? So what would happen is these instructions within the foo will change to address of GBL, which is specific to my P1, right? So my process P1 loaded the shared library at address 500. So the address of GBL, let's say for simplicity, is 500. So all these instructions would be modified by dynamic linker to address 500. Okay. Now what happens is, as soon as I make it specific to my process, I can't actually share it if some other process also wants to use the same code, right? So let's say I have a.out, okay? I run it, then the shared library gets loaded. Address of GBL happens to be 500, so the instructions in function foo are modified to point to 500. Let's say now b.out runs, which also requires the same shared library code, right? But it ends up loading that shared library at location 900, because that process might have a bigger text segment to begin with. So the shared library was loaded at some different virtual address. So now I can't use the same code which was loaded in the memory, because that was pointing to 500 and this is pointing to 900, and both of them are running concurrently, right? So I lost my ability to share the code. So I have the same problem which I had with static libraries, that if the static library is linked to one exe and then other exe and then other exe, each of them have a separate copy of that code, right? So one of the things which shared libraries want to do, and the reason they exist, is we want to share this code at runtime. So physically in RAM, we want only one copy of function foo to be loaded. And all the processes that are using that must refer to the same copy, same physical copy, okay, not necessarily the virtual address. Any questions on this concept of why we have a problem with this relocation? Okay, now how do you solve it, right? We can think of multiple ways of solving it. Let's solve it by saying that, okay, why not have every shared library a fixed address? So let's say I say that libc shared library is always loaded at address 500 only, and no matter what happens, it is always loaded at address 500, right? Then some other shared library is always loaded at address 2000, and so on. Obviously, you can see that it's going to not work because it's very inefficient use of address space. And as the number of shared libraries increase, it would get into problems. As each shared library adds new functionality and its size increases, it's not going to work, right? So this scheme works on paper, doesn't work in practice, because there will be just many shared libraries and you can't get a reservation. It's like saying that some band width and some spectrum band is reserved for me, and that needs to be done globally. So you can imagine whether you can actually get it, right? So the solution to this is something called as position independent code, right? So can we generate code in a way that no matter where it's loaded, it is always same, right? If we can achieve this somehow, so the code is independent of the address where it starts, then we should be able to share it, right? Because if you load the program at 100, it is exactly same. If you load it at 2000, it is exactly same. It is loaded at 5000, it is exactly same. Then you should be able to share it, because the program doesn't change no matter where it's loaded, right? So a way to do this is by doing indirection, okay? So one of the things which you should realize is relative addressing, which is PC relative addressing, is always position independent, okay? So for example, in this particular case, if I'm doing jump to a label done, right? In most processor architectures, the instructions like JMP, call, etc. will take PC relative address. That means they will take the difference between the current instruction versus the target. So we are not actually jumping to the address of done. We are jumping to the address of done relative to the current instruction. Okay. Now the good part about this PC relative address is no matter where the program is loaded, it is always same, right? So even if the dot text gets loaded at 1000, this jump would still work. If you say it is loaded at 5000, it would still work, because this, you are not adding anything in between here. So the offset kind of remains same, right? Section relative is essentially if you say it is relative to a section, and unfortunately this is not position independent, because remember, when there were multiple text sections, linker kind of merged them together, right? And you may have to change the addresses to cross these things, okay? So we need some way to do a relative addressing instead of the absolute address that we were so far using, okay? So remember what happened during linking. So linker merged things together, right? And after merging, linker knows what is the size of each text section and so on, right? So what we can actually do to achieve position independent code is somehow use this information to actually refer to the variable, okay? So let's say if there was this move instruction, right, which was referring to this data variable, right? And I had this, originally it was a different offset, but I know when this text section was added, what should be the relative offset of this, okay? I'll give an example. So what shared libraries do is they create an indirection via something called as global offset table, okay? So think of it this way: there is a separate table which is holding addresses of all variables. Okay. And the start of this GOT or global offset table is always fixed after the text sections. Okay. It is part of the data section, but it always is at known and fixed location relative to a text section. So what you can do is, instead of patching this, instead of modifying this move instruction, so let's say this move instruction needs address of var1. Instead of directly modifying this instruction to use var1's address, you could actually go via GOT to get that address. So for example, you can actually, so you can actually change this move instruction to first load the GOT address, right? And GOT is known at a fixed relative offset. So you should know that GOT is at this PC relative offset from this instruction. And within that, you know where is var1. So you can simply load that address. And what you have avoided is you have avoided the need for creating an absolute reference, absolute address reference in this text section. Okay. x86 unfortunately doesn't have a way to create a PC relative reference. So there is a trick which I'll skip over for now. But essentially, you will see code something like this. So what you can do is you can call some function. Okay. And this function call, remember what happens in the stack, the return address gets pushed. So whenever you call function on x86, it implicitly pushes the address of next instruction on the stack, which for the return. Within this function, what you can do is you can actually save that address, which essentially gave you the address of the current instruction, and you return. And then once you get the address of current instruction, you can actually compute the address of GOT, and then you can get the address of var1. Does that make sense, or was it too fast?
This was, in my opinion, very quick summary, but very good.
Yeah, so if I have to, I think if you simply want to get the concept and leave out the specifics, I think fundamental thing you have to remember is the problem we are trying to solve is within the text section, you don't want absolute addresses to be present, right? And the way you achieve that is if you can somehow say that you have some separate table, okay? And you know how to, what is the relative offset of that table from every instruction, right? Then instead of getting the absolute address directly patched via relocation, what you can say is I will get to my global offset table to load the address. So we have created indirection by, instead of move instruction directly referring to var1, it first refers to GOT, and from GOT it gets the address of var1. And the good part about this is there is no relocation that is needed on the text instructions, because GOT is always at a fixed relative address, so you know how to access it. So there is no need to relocate the text section or modify the text section. And if you keep it same, that essentially means you can share it across processes. Does that make sense? And essentially what you can do is to populate these addresses which are still not known. You will have to have relocations, but essentially the relocations on data segments are fine, because those you cannot anywhere share, because each process has its own private data and you cannot share it with other processes. But the text section gets relocation free. So remember, the aim of shared libraries was to ensure there is no relocation on the text section. And we achieved that by saying that we will go via an indirection, and that indirection was achieved by referring to data which was at fixed PC relative offset. So we could refer to it without a relocation. And the data that was actually there had relocations, but that was in data section. So the text section was always C. Does that make sense? Or there is more complicated stuff when it comes to functions, but I think I'll skip it for now because I think it's just getting too fast to grasp. I'll anyway share these slides which do have illustrations, so hopefully they will help you understand things. And if not, you can always drop me an email for if you have any more questions. But I would probably stop here, and if people still have energy left for any questions, I can help answer.
Sir, I have a general question. What are some good resources to learn about this? But because you really don't find all this stuff in the usual places.
Correct. Unfortunately, that's one of the problems, that it's very hard to find references to this. You might find some good material on if you search for these terms, you would find probably a lot of blogs which explain it. Okay, so for example, if you search for something called as position independent code, you would get a lot of blogs written by various people who can explain this, but I don't think there is a book or any single source of reference which covers all of this. Because one of the things which you have to understand, and the reason why this doesn't get into academics a lot, is because a lot of this is more engineering oriented, right? And a lot of it will keep changing as we come up with more innovative solutions for solving these problems. So there is not much theoretical background to it, unlike compilers, right? If you look at the compilers, they come up with a lot of theoretical foundations. They have a lot of proven theorems, techniques, etc., which makes sense to put it in academics. All of the things which I talked about today are very much implementation oriented. ELF chooses to implement things this way. Windows might choose it to do it different way. Android might do it in third way. And each one will be correct in its own context, and each one will have its own reason why it is doing it that way, because they have different constraints to follow, right? NVIDIA GPUs, for example, follow very different philosophy on how we implement our loader and linkers. Okay, not because we don't know this, but because we have different set of constraints and our environment is different in which our programs run. So some of these things may not apply in that context, which is where it gets very hard to find academic covering this topic, right? But what I tried to cover was mostly on Linux x86, which is probably the most common platform everyone would be dealing with. So it makes sense that everyone knows at least this much, right? But yeah, I think a better way I would suggest is, if you want to learn more about this topic, I would say Google for these topics, and you will find probably good blog entries which explain this. But I don't think there is a book or any reference material which covers this topic as a whole. There is a book called as Linkers and Loaders, which covers a lot of it, but it is slightly older. So you may not get all the latest and greatest information in that. But it does cover principles to a good level.
Okay, thank you. Thank you.